This is group A5 with Peter,
Jory,
Alex,
Isa.
and today we will be talking about function growth and an analysis of runtime. This video can also be found on www.a.mov.com. We're going to go over comparing functions and analyzing why some grow faster than others, as well as describing the general order of functions, and lastly showing how after being given a function, we can determine its worst-case time complexity. This video assumes that you have prior knowledge regarding big O and big theta notation, so if you don't, I would refer to the website www.knoatom.com for more information. As you may know, some functions grow faster than others. We can determine their relative rates by taking the limits as they go to infinity using some calculus and L'Hopital's rule. So I can show you some limits of functions, like for example, if you take the limit as n goes to infinity of log of n over 1, it equals the limit as n goes to infinity log of n, which equals infinity. This shows that log of n grows much faster than 1. And we can also take the limit as n goes to infinity of n squared over n, which equals the limit as n goes to infinity of n, which also goes to infinity, proving that n squared grows much faster than n. On this graph, we can show the 7 most important functions. So the lowest on the growth scale would be 1, which is just a straight line. The next one would be log of n, followed by n. And then we have n times log of n, followed by n squared, and then 2 to the n, and lastly n factorial, which grows the fastest. Remember that this scale is logarithmic. In computer science, an algorithm is used to solve problems. The algorithms follow certain function behaviors and are analyzed based on their runtime and complexity, based on how many operations are used. It is described in number of operations because different computers perform basic operations at different speeds. We will now analyze the worst case time complexity of the binary search algorithm. By worst case performance of an algorithm, we mean the largest number of operations needed to solve a given problem using this algorithm on input of specified size. Worst case analysis tells us how many operations an algorithm requires to guarantee that it will. We now specify the steps of the binary search algorithm. To search for the integer x in the sorted list from a1 to an, where a1 is less than a2, etc. is less than an, begin by comparing x with the middle term, am, of the list, where m equals the floor function of n plus 1 divided by 2. If x is greater than am, the search for x is restricted to the second half of the list, which is am plus 1, am plus 2 to an. If x is not greater than am, the search for x is restricted to the first half, which is a1, a2 to am. The search has now been restricted to a list with no more than the ceiling function of n over 2 elements. Using the same procedure, compare x to the middle term of the restricted list, then restrict the search to the first or second half of the list. Repeat this process until a list with one term is obtained. Then determine whether this term is x. Assume that there are n equals 2 to the power of k elements in a given list from A1 to AN. K equals log of n in this case. The list can be considered part of a larger list with 2 to the power of k plus 1 elements. At each stage of the algorithm, I and j, the locations of the first and last term, are restricted and are compared to see whether the restricted list has more than one term. If I is less than j, a comparison is done to determine whether x is greater than the middle term of the restricted list. At the first stage, the search is restricted to a list with 2 to the power of k minus 1 elements. So far, 2 comparisons have been used. The procedure is continued until there are 2 to the power of 1 elements. And finally, when there's one term left in the list, one comparison tells us that there are no additional terms left, and one more tells us if this term is x. So totally, we have 2 times k plus 2 comparisons, which equals 2 times log of n plus 2 comparisons required to perform a binary search when the list being searched has 2 to the power of k elements. So at most, there's 2 times the ceiling function of log of n plus 2 comparisons used, which is the worst case scenario. So the complexity is big O log of n. For another example, we will also analyze the worst case time complexity of the bubble sort algorithm. The bubble sort sorts a list by performing a sequence of passes through the list. During each pass, the bubble sort successively compares adjacent elements, interchanging them if necessary. When the ith pass begins, the I-1 largest elements are guaranteed to be in the correct positions. During this pass, n-I comparisons are used. Consequently, the total number of comparisons used by bubble sort to order a list of n elements is n-1 plus n-2 plus all the way to 1, which in turn equals n-1 times n over 2. Note that the bubble sort always uses this many comparisons because it continues even if the list becomes completely sorted at some intermediate step. Consequently, it's big theta n squared complexity. Remember that this video and many other videos like it can be found at www.a.mov. We would like to thank you for watching this video. Group A5 out.